Hello everyone, this is Jeff from the Ozark Mountains in Missouri, USA. You remember last time we got this TRS-80 Model 100 function. And hot damn. See if I can hold this up here so you can see what is going on. Functional. Now as you can see, I've not put it back together yet because there's some more work to do. What we found on that was the standard RAM module, which was soldered to the board, was bad, and we took that out and replaced it with one of the optional RAM modules, which had been socketed in there, and that's at least got it functional. So this time we're going to completely replace all the electrolytic caps and replace the old NiCad memory backup battery with the Super Capacitor. Now, the sharp-eyed among you will notice that got another whole one of these. My fellow in Kansas City was selling this. He's nice enough to put it in a box and ship it to me for a reasonable price, and I thought, well, I might need parts. I wasn't sure what was wrong with this one yet. So I bought this one, and fortunately or unfortunately, depending on your point of view, it works. But I'm pretty sure it's going to need the caps replaced. So, oh, that's even beeping at me. Oh, it's holding on the space bar there. So, at any rate, probably won't do anything in particular with this one. Maybe hook the two together at some time, or maybe fix this one up for a future giveaway. So, you never know. Let's get started. Now, one thing that has kind of driven me crazy since I first took this thing apart, besides managing to snag this ground wire on everything, is these little rubber donuts that keep this shield in place. These are a little loose and they fall all over the place. A couple of them was missing, and I replaced those with, let's get that a little closer, maybe it's still in focus. It's one of the little rubber bushings that's used when you put a wire through a metal case, that type of thing. This one is about 3/8 inches, 10 millimeters on the inside, 6 millimeters, 1/4 of an inch on the inside here. The larger dimension was this part, and if you stretch it enough, it will stay on here, which you can't see me doing because my fingers are in the way, but stretch it enough, it'll stay on there like that. These others are a little loose and they fall off all the time. So what I'm going to do is take a little of this, see if you can see that, E6000 glue. This is nice. It doesn't get rock hard, so you can remove it later. Get this dry stuff off the top here. Take a little of this glue, dab it on the inside of these things, just like that, just a little bit, so it'll stay in place. So, you may recall from last time that I replaced 5 or 6 of these electrolytic caps on here, the ones that were leaking, and there's a few here in the power supply section that were bad. I think these 3. This was supposed to be a 33 microfarad. I didn't have that, so I put 3 10s in parallel, which was enough to get it going temporarily to troubleshoot it. So I got a bag of capacitors here from Mauser, and I'm going to replace all these capacitors, the electrolytic capacitors that is in here. And also in this bag, if I can find it, are a couple of super capacitors. These are 2.5 farads, rated at 6 volts, and they should fit in here where the original NiCad did, and should charge up and back up the memory just about as long from what I can figure. So, okay, so now we've got our board here, And last night I got a little carried away. I decided it'd be nice to kind of have a map of where all these different capacitors were here on the board to make it easier as I was replacing all of them. So I did this. I took the spreadsheet that I had originally to do my order, where I got the NiCad part numbers and the package sizes and whatnot, and I took a picture of the board layout from the service manual that I found online and did a color and letter coded map of where all the different capacitors are. That might be a little overkill, but there's a few of them where they're very similar values. You know, maybe the voltage is different or something like that. So this will help keep all that straight, because there's, I don't know, a dozen or more. And I got my bag of capacitors and went through and sorted them out by the lowest capacitor number to highest and marked those numbers on the bag, and then, you know, double checked it against my list here, so I should be able to keep these straight. And then get the soldering iron turned on here, and I've got my trusty let me get it here. I've got my trusty heat gun. You saw me use this before to preheat some of those areas where it's hard to desolder the capacitors because of the ground plane they go into. And we'll get busy and replace all those capacitors. Oh, one thing I'm going to do first is go ahead and desolder my temporary backup battery here. I don't want to be, you know, soldering and desoldering on this battery still powering the memory, so we'll get that off of there first and set it aside. So I removed the battery, like I said, and one thing I also did, if you can see my light here, is I turned my light over this way, get down where you can see it, and shined it through the board so I could see where the capacitors were, and then marked them with a black mark so I know where each one is. Makes it a little easier. So now we'll get busy removing these. Now the first ones I want to do are A, B, D, and E on my list here, which are all the same ones at 10 microfarad, 16 volt. And they are right across here. Just about in a line, so I will do those first. I'm going to preheat the board a little bit. Even with all that prep and heating and whatnot, it was still kind of tough to get those out of there. Yeah. That's it. Here we go. C49, 50, 54, and 55, which matches the map. Okay. Now, get these positioned in here with the negative stripe in the right orientation. Okay. Now I've got these 4 first new capacitors in there. Made sure that the negative stripe was pointing up as marked on the board. Some of the solder mask kind of chipped off here as I was cleaning, even the first time I was cleaning, so it's best before you pull the capacitor out to have a good look at it to see which side the stripe is on. Like on this one here, it is really difficult to tell. So I have to see when I pull that out. So now we'll flip this over put just a teeny tiny bit of rosin paste flux on the leads, and we'll go ahead and preheat that a little bit. Okay, 4 down, 13 more to go. Now I'm going to pull out C52, which is a 1 microfarad 50 volt. Looks like it might be a non-polarized electrolytic. Can't really tell. It's a conundrum. So, as you know, when I was replacing the capacitors on the TRS-80 Model 100, I realized I had misordered some. There were 4 of them that were supposed to be non-polarized electrolytic capacitors, which you can think of as 2 regular electrolytic capacitors placed back to back in series. So you get half the capacitance, but they operate as a non-polarized type capacitor. So you get relatively high capacitance, and you can use it in an application where you've got current that's flowing both directions. So here's the map. That is the same. I did add some letters in here to the color coding to make it a little simpler. And here, everything I've highlighted, these 4 are the non-polarized capacitors. This one here in this kind of peachish color, C52, which is right here, that was specified as plus 75%, minus 10%. On all the other ones that had that sort of specification, I was able to find a plus or minus 10% that would work. This one I was not. It's in the part of the modem circuitry, which we'll look at here in a second, and I'm not sure how important that is. I'm not sure I'm ever going to use the modem, but I had to go with a plus or minus 20% part here, and we'll measure that before we put it in and see if we happen to fall within that plus or minus 10% category. Now, this is part of the schematic, and here is the modem connector, and we have this RXM line which comes down through a switch, goes through a series of op amps, and down here we get to C52, which you see looks like kind of a funny capacitor symbol. That means it's non-polarized, and it also says NP right here. So I reordered the capacitors that I got the wrong type of, as well as another whole set for the second Model 100 that I got from Craigslist. Those came in, and I marked those like I did before, that they're for the M100 and what location they go in. Then I separated the packages of the ones that I need to replace on this board. And we talked about, I wasn't quite sure what tolerance we're going to wind up getting for C52, because it was originally specified as plus 75 minus 10%, and I couldn't find a non-polarized electrolytic close to that, so I had to get plus or minus 20%. So I pulled those out and connected them up to my little cheap tester here. Measured both of them, and I'll do a close-up here of this, but it says that the capacitance is 1048 nanofarads, which is 1.048 microfarads, so that's well within range, even considering that this little guy isn't going to be spot on accurate. So I think we're doing okay there. Okay, we have one other thing we need to get taken care of before we get this thing buttoned up and back in the case, and that is the memory backup battery. Now, as you'll recall, the system expects that there be some code that is permanently stored in the static RAM, so we need this backup battery. This one is dead. It's the original one that was in there. It is a NiCad. I took it out and I pulled up the anode side of D11 here, which helps control the charging to that NiCad, and I put in this non-rechargeable lithium battery here. This is basically a stack of coin cells. So put this in there temporarily while troubleshooting, so we had some battery backup for the static RAM. That wasn't a permanent solution. Now, that NiCad battery is still available, but I didn't want to put an old NiCad in there. There's also nickel metal hydride batteries available, which are the same form factor. That's an interesting possibility. They tend to self-discharge quite a bit, which kind of defeats the purpose of a long-term memory backup battery. If you have the one RAM module, that battery will back it up for 4 weeks, and if you've got all 4, you get 1 week. And that's that time period is when you don't have the AA's or you don't have it plugged into the wall. What I did is I ordered a 2.5 farad 6 volt super capacitor. That was only, I don't know, maybe $5. It wasn't very expensive, and I bent the leads kind of like so. Put a little heat shrink tubing on there, so those will plug right into the original holes, and I'll put some glue on that, like that, to hold it in place. And there's plenty of room in the case in there for it like that. Solder that in there, solder in the diode that I pulled the leg up on. The original NiCad charged about 5 milliamps, so this should do the same, so it should work just fine. So let's get this soldered in there now and get the board of final cleaning. The super capacitor is installed. We have it just right here, and I've got some leads clipped to it that go to this voltmeter here, so we're going to measure roughly how fast it charges up. And this set of clip leads right here goes to another voltmeter, which is out of the shot of the camera, and that's just going to measure the voltage that is developed down here across the RAM. I took the RAM module out, but that voltage should be fine. I believe the RAM is good up to about 6 volts, so we should definitely be fine. I've got my bench power supply set up for this, so I'll go ahead and get it turned on. Bench power supply set to 6 volts to simulate 4 AA batteries. The power switch here is turned off. I've got the keyboard and display disconnected. I'm not worried about it running. It's not going to run because the RAM's not in. I'm just worried about the battery charging up. So as soon as I turn on the power supply, we should see this reading here start creeping up. And I'll tell you what the other meter that you can't see, I'll tell you what it's doing. Okay, power on the power supply. Power is on it says we're drawing 0 amps there. Something's not right. Oh, I bet I have the memory switch turned off on the bottom. I didn't double check that, so I want the main power switch off anyhow for this. I'll tip this up. Yeah, okay. This memory power switch on the bottom acts kind of like a main power switch. I'll turn the power supply output off. I'll turn that guy on. Okay, the best laid plans. That was rather anticlimactic. Okay, so got everything hooked up just so. turn the power supply output on. Okay. Still got nothing. What's going on here? Okay, we do have an output from the power supply. I'm just not making a good connection there. I'm not blocking the shot, I apologize. Oh, okay, I wasn't making a good connection on the capacitor. Alright, hopefully you can see now that it is ever so slowly charging. As I recall, this was a feature, air quotes, feature, of the original NiCad battery, that if it was completely dead, you had to wait several minutes for it to charge up before you could run the machine. Now the second meter here is the one that's measuring the voltage at the RAM module, is showing about 150 millivolts, so it's about 50 millivolts below the capacitor value. To give you an idea how slowly this charges, it has been going about an hour now and is up to about 2.8 volts. So it'll take about another hour for that super capacitor to fully charge. That's because it's only charging with about, 5 milliamps or so of current. So not a lot. It'll take quite a while. Just a quick update here. That super capacitor's been charging nearly 3 hours now, and it is up to 4.23 volts at the capacitor, and then down at the memory module power connection it is 3.8 volts. Okie doke, it's been a little over 12 hours. The meter here is the one that's showing us the battery voltage. That's 5.27 volts. And the other meter, which is measuring the voltage at the RAM module, is 4.85 volts. So that's about 0.42 volts or so drop across that diode that's between the battery and the RAM module. So that is bringing the voltage down at the RAM module to well within the safe range, so we'll be okay there. Oops. I've got the bench multimeter hooked back up to measure the voltage at the first memory module, and I noticed something interesting. See if I can get zoomed in on here so you can see it. Well, this is without the memory module in there, so it's just the impedance of the meter causing the current drain, or it's something inherent in the capacitor or board. But every couple seconds it drops about a 10,000th of a volt. I was a little confused as to what I was seeing as far as the capacitor seeming like it was self-discharging. When I had originally started out trying to figure out what size of supercapacitor I might need, I went to this website, and there's a link below, which I found helpful. But, the super cap wasn't lasting as long as this formula predicted. And after some more reading and testing, I realized what this column in the data sheet for the supercapacitor I got, what this was telling me. So here is the part number of the supercapacitor I got. It's 2.5 farads, 6 volts. And this here says 30 microamps. It's DCL max at 72 hours. Well, what that's telling us is that after 72 hours, this capacitor is going to have a self-discharge rate of 30 microamps, which is pretty large actually. And, why in the world would they rate that after 72 hours? Well, the reason is that the discharge curve for the capacitor is nonlinear, but it does flatten out after 72 hours, so that makes it simpler to specify, and it looks a little better because they're ignoring that higher discharge rate initially. So after I figured that out, I found this PDF on Mauser's website, and there's a link below which provides a couple different formulas for trying to estimate the discharge rate for the capacitor. I found this PDF really helpful, actually. So I took what I had learned and filled in some more information on my spreadsheet, and tried to predict the volts per hour discharge, using two of the different formulas there, anywhere from 4 thousandths of a volt per hour to 6 thousandths of a volt per hour. And then I actually measured here, both powering one single RAM module and without RAM. And by saying without RAM, what I'm meaning there is I charged up the second super capacitor, and it's connected to absolutely nothing, and measured it using my bench meter and disconnected it and let it set for a number of hours. So, the super capacitor by itself, in about the first day, it dropped about 41 thousandths of a volt per hour. In the next day and a half, it dropped down to about 17 thousandths of a volt per hour. And I actually took another measurement this morning, and it dropped a little lower than that. Now, with a single RAM module in there, you'll notice that its first day of drop was about 61 thousandths of a volt per hour. So powering the RAM does make a difference, but the self-discharge rate of the capacitor kind of overshadows what the RAM itself is drawing. So based on this, I tried to predict how long that the static RAM will be powered based on the number of RAM modules that were installed. And it goes anywhere from about 2 days with one RAM module to 1 day with all 4. Since the battery backup, or in this case our super capacitor backup of the static RAM, is only used when the AA batteries are being changed or you have no external power. In other words, it's only backing up the RAM when there's no other power source. When you have another power source, the AA's or the external power, then that's what's powering the RAM, even when you have the computer turned off. So given that it's kind of a backup for when you're changing batteries, I still think this is okay, but I'm a little disappointed it's not better. Now, I did find that at the university where I work, we have a piece of test equipment that's designed to test really low leakage currents like this. Of course, it's kind of difficult to use because there's a lot of programming to set up to apply the charge current the way you want it and then measure it over an extended period of time and data log it and that type of thing. But if I have the time, I will look into how to program that to set it up and try to profile this super capacitor and try to get a better idea of what's going on here. Well, you may have noticed I took it back out of the bottom half of the case again. And the reason is I forgot one thing. I wanted to shoot some contact cleaner with a little lubricant into each of the switches, and of course one of them, the memory switch, is here on the bottom, so I had to pull it out to do that. So just shoot some of that in there. Arc it back and forth. Do the same for the rest of them. This stuff is a contact cleaner, and it's got a little dry lubricant built into it to help keep the switch working, moving smoothly. Okay, so now we've got that done. I'll clean up my mess here and we'll get it put back in the case. of these bottom screws are the same, except for the one in the center, which had that little standoff on it. I imagine that's to keep the keyboard from flexing down. I always like to get all the screws started first, then go back and snug them all up. That is a slight miscalculation right there. Okay. That just barely fit in there. Okay, so if you're doing that, you'll want to pull your capacitor down toward the bottom a little more than I did. Here's a little bit of a rubber bumper on that I didn't notice before. Not exactly sure which way around that went, but I don't know that it makes a big difference. And snug up the rest of these screws. I am regretting gluing that capacitor in there the way I did. So although that glue shouldn't be very conductive, there might be just a tad of leakage current. Should have thought of that beforehand, or maybe put a little Cap-Tan tape over that section of the board before I put the dab of glue there. That would have worked too. I'm not setting a good example. I do have my mat grounded, my anti-static mat. I did not put my wrist strap on, so I'm kind of setting a bad example for y'all, but got our standard RAM module plugged in there. I'll turn it on and test it with that here in a bit, and then I'll plug in the other optional RAM that I have. Okay, I've got the screen hooked back up, and I've got the bench power supply hooked up to the battery terminals from the back, so I can kind of close this here when I'm done. I also want to let the super capacitor charge back up because I've had it self-discharging all day for testing purposes. So the first thing I will do here is, let's see, the bench supply is off, the power switch on the computer is off, board is mounted in here properly. I'm going to turn on the memory power switch. Okay. Okay, so that's correct. I'll turn on the bench supply. It's not really drawing anything, which makes sense. I'll hold down brake and control. Turn on the power switch and hope it still works. Flip it over and see what it's doing. Hey! It's January 1st, 1900. It not only works, we went back in time. Awesome. Okay. So I'm going to turn it off. And close this up kind of like that, just for now. So I want to let the super capacitor charge off my bench power supply here for, I don't know, an hour or so, just to top it back off. And I will put the AA's back in it and the second RAM module and just get busy trying to learn how to use it. Spent all this time working on it, I should learn how to use it now. We found out that the standard RAM module was bad, but I wondered why. Now, there are 4 separate 2K RAM chips on the module. All the address and data lines are wired in parallel, and the chip selects are used to differentiate which chip that you're writing to. Unlike other computers, say the Commodore 64, where you have 8 RAM chips and each one of them has a bit, each of these RAM chips are mapped to all the address lines, and you use the chip select to decide which address space you're writing into. While looking for something else entirely, I came across this wiring diagram of the RAM module in the technical manual. And I figured out, we'll see on the next page, that I would be looking for chip number 3, but I didn't know what chip that was on the module. Looking at the schematic, this is the standard RAM module here. This is the chip select that's going to the particular RAM chip we're interested in. And according to one of the fellows on the Model 100 mailing list, if address line 4 was messed up, the RAM copy might be going right over top of the stack. So I thought I would concentrate on that. I also found this in the technical manual, which is an illustration of how the RAM is decoded. So we have our address lines here, 12 through 15, and that's being used to gate the address select lines if it's a write into the RAM area, and as well as select which particular RAM chip to use. This particular illustration shows the very end of the RAM from F800 to FF, which is illustrated by this dashed line showing that's what's active. So the space we are interested in, or the RAM page we are interested in, falls within the F000 to F7FF, which would be the 2K just below that. It's right here, which is the CE15 selection line, which is why I had addressed this over here. So then the next thing we'll do is ohm out the RAM module and make sure all the lines are going through, and pay particular attention to address line 4. So to test out the suspect RAM module, or I guess it's not suspect, it is bad, just didn't know why. I placed it and the good one on a little piece of prototyping board here. It's able to ohm out each pin on the module to each pin on the IC, and also by looking at each chip select, figure out which IC was which. So I found out that all the lines went through to the bad IC, which was number 3, which I think, well, it's one of these two. I don't remember which off the top of my head, but all the lines went through to it, and it's still not working right. So I've got a bad RAM chip there, and I see there's some on eBay, but I'm kind of hesitant to buy some, but I might just try and fix this RAM module. Well, I hope you've enjoyed this journey into fixing a TRS-80 Model 100. We did get it running. We had to replace a whole handful of capacitors, a NiCad memory backup battery, and most importantly, bad RAM module. But we did get it going. Along the way we learned something about super capacitors, troubleshooting with a logic probe, and in general a bit of appreciation for the engineering that went into these things back in the 80s. Stay tuned for some more episodes. I'm not sure what we'll be working on next. Maybe another Commodore. Maybe I'll finally get my Commodore 128D all set up and we can have a look inside that. If you have any ideas or things you would like to look into, or questions, please leave them in the comments down below. Also down below are some links to the things I talked about in the video. Oh, one other thing. Please consider subscribing, and if you do, click on the bell icon down below so you'll be notified when I post a new video. I sure would appreciate it. Thanks. See you later.